Hi there, my name's Dr. AJ Kumar, PhD. So I have this playlist called Readin, Readin apostrophe. And so far I've read 3 sections out of Artin's book called Algebra. And the next section is on something called the determinant, which if you've taken a bit of linear algebra ever, you know what the determinant is. And I feel like most people, even most people who graduate with a degree in mathematics, don't really have a good understanding of what the determinant is. So there's a fact that you learn, which is that if you have some square matrix, what's going on? Let's switch to white. You have some square matrix M. So I'm just going to take 6, 7, 3, 2. Okay. The determinant of this is 6 times 2 minus 7 times 3, which is 12 minus 21, which is minus 9. So the determinant of M, sometimes you write it like that, in this case is minus 9. And since this is not equal to 0, you know right away that this matrix has an inverse. And what is an inverse? What do I mean by an inverse matrix? So what I mean by this is there's some other matrix, let's call it N, such that N times M is the identity matrix. So this is the formal definition, or this is equal to M times N. And so it doesn't matter which order you do the multiplication. That's what this means. That's what an invertibility means. And the only types of matrices that can even be invertible are square matrices, and that's a whole topic. Now, I'm not going to try to cover all of linear algebra. There's plenty of playlists out there that cover a lot of linear algebra. There's one by some Russian guy. The channel is called Math the Beautiful. That's a very, very good playlist. Then Norman Wildberger has a playlist on linear algebra, which I have not watched, but I highly recommend Norman Wildberger. He's my favorite math channel on YouTube. So I would look at Wildberger as well as Math the Beautiful. And then also Gilbert Strang. So what am I going to talk about? So the next section is about determinants, and the next section in Artin is about determinants. And I don't feel like I read this section beforehand, and the arguments are just, they're correct, and if you really follow them closely, they make sense. But I don't feel like you get a strong intuition about what's going on. And so before we read Artin's section about determinants, I want to talk about them and explain what is going on. To some extent. You can't explain everything going on with determinants just because it's such a rich subject, but you can explain a little bit. So let's step back a little bit and just talk about the most basic problem in linear algebra. I gotta put the microphone down because I gotta write. We're gonna talk about, where does linear algebra start? So what even, you see a matrix, it's some array of numbers, but let me instead frame this in a slightly different way. So let's say that I have two variables x and y, and 6x plus 7y is equal to, and I'm actually going to leave the other side of the equal sign blank for a minute. 3x plus 2y is equal to, it literally doesn't matter what numbers I put here. The fact that this matrix is invertible means I can put, I'm just going to put 2 and minus 4. It literally doesn't matter which numbers I put here. This will always have a solution because the matrix is invertible. Now, it's going to take a little while to see why that's true. But and you can tell that the matrix is invertible right away by computing its determinant. But I want to start from the basics, from high school algebra. What is going on here? Okay, so what is the traditional way you solve this? Well, the traditional way is something called Gaussian elimination. And I'm going to show you a slightly let's just walk through this using the high school algebra method. So first thing we're going to do is take the first equation and what should we do? Let's take the first equation and subtract the second equation. So that'll give us 6x, or correction. So subtract the second equation from the first equation, and that'll give us 3x. Is that what I want to do? What you want to do is get one equation that says x is equal to something and y is equal to something. So yeah, let's just do 3x plus 5y. So minus the second equation is equal to 6, I believe. And rewrite the second equation. 3x plus 2y is equal to minus 4. Okay, well, we can actually eliminate by doing another subtraction. So we can eliminate x from the first thing. So we can get 3y is equal to 10. And then we still have 3x plus 2y is equal to minus 4. Okay, and so I'm going to take the second equation and multiply it by 3/2, 3 over 2. So we still have 3y equals 10. Better ones. Still working on better ones. 3y is equal to 10. And then 3/2 times 3 would be 9 over 2 x plus 3y is equal to minus 4 times 3/2. It's going to be minus 2 times 3, which is minus 6. Okay? Subtract the second. So take the first equation, take the second equation minus the first equation. Because all we're doing is adding equals to equals. And notice that when I take an equation, so there's two operations I'm doing here. I'm either taking one equation and adding it to another equation, or I'm taking an equation and multiplying it by a constant. Those are the operations. Okay. And that recognizing that those are the two operations is what is going to be important. I can also transpose the two equations, but I will list the explicit symmetries later. Okay, so 3y is equal to 10, 9/2 x plus 3y is equal to minus 6. Okay, so still right, 3y is equal to 10. And then we get 9/2 x. Well, subtracting the third equation is equal to minus 6 minus 10, so minus 16. Okay, so from this we can deduce x is equal to whatever minus 16 times 2/9 is, whatever that is. And then y is equal to 10 divided by 3. Okay. It's a pretty straightforward sequence of steps. Okay. I'm going to rewrite this as a matrix problem and just solve it in parallel. Okay. And I'm going to do this a little bit differently. So the original problem, 6x, so 6, 7, 3, 2. That's all we have to remember. And then 6, 7, 3, 2. And 2 and minus 4. Okay. This is the matrix way of writing the problem. Again, I'm assuming you've seen linear algebra before and you're familiar with the basics of how to multiply two matrices together. Okay? Right, I'm assuming you're not a baby. Now, what I'm going to do is I'm going to write this in kind of an odd way. I'm going to instead write, how should I set this up? Okay. 6, 7, 3, 2, and then I'm going to put a dotted line here, and I'm just going to write down the identity matrix. Okay. Now, what I'm going to do is sort of replicate the series of steps I did before. So take the first matrix, take the second equation, and subtract it from the first equation. Okay. So what I claim is that each one of these operations that sort of does an allowable transformation to the system of linear equations, you can actually get that by multiplying by a matrix. And I'm going to tell you what that matrix is. And you can actually cook up the matrix really easily. So what we're going to do, take the second equation, so first equation minus the second equation. So take the second row and subtract it from the first. Well, the way you cook up a matrix that does that, and I'm going to call this matrix gamma. Well, gamma has this property that gamma is equal to gamma times the identity. So if you just imagine whatever this matrix does to the identity matrix, that's what gamma is. So we look at the identity matrix and subtract the second row from the first. And so that is going to be our first matrix called gamma 1. And this is going to be the matrix 1, minus 1, 0, 1. Okay. And then we'll subtract the second equation. So we're going to get 5, 3, 5, 3, 2. And then we're going to do the same thing to the other side over here. So okay. Now, let me just show you very briefly. Gamma 1 times, let's call this M, and this is the identity matrix. So let me just compute gamma 1 times M explicitly to convince you that this is actually true. So this is 1, 0, minus 1, 1. And then I like to multiply matrices by putting 6, 3, 7, 2, because then it's easier to visualize. Okay. So this entry will be 1 times 6 plus minus 1 times 3. So 1 times 6 plus minus 1 times 3 is going to be 3. Right? 6 minus 3. 7 minus 2 is going to be 5. 0 times 6 plus 1 times 3 is 3. This will just copy, the 0, 1 just copies the row. So we get the same answer in either case. Okay. Now, this is gamma 1, oops. This is now gamma 1 M bar gamma 1 identity. Now, the basic trick we're going to do is we're going to have a bunch of matrices gamma sub n down to gamma 1 times m such that we get m such that over here gamma n down to gamma 1 times the identity matrix and such that this is the identity matrix bar something else. Well, this now implies, so if you, that the, let's call this gamma hat, let's call it, is equal to gamma n, the product down to gamma 1. Well, if you take gamma hat and multiply it by m, you get the identity. Then gamma hat, this must be the inverse of m. So at the end of this process, the thing we're going to get on the right side of this dotted line is the inverse matrix of m. Okay? Does that make sense? So let me just copy what we had before. So 3, 5, 3, 2, 1, minus 1, 0, 1. So this is all we're doing. This algorithm is called Gaussian elimination. Okay, so then we're going to do it again. So gamma 2 is equal to 1 minus 1, 0, 1. Same thing again. So in this case, we're going to get 0, 3, 3, 2, minus, or 1, minus 2, 0, 1. Okay? Now, what we're going to do is we're going to take the second equation and multiply it by 3 over 2, correct? That was what we did before. So, well, what we do is we imagine what happens to the identity matrix. So again, gamma 3 is equal to gamma 3 times the identity matrix. So whatever gamma 3 does to the identity matrix, that's what gamma 3 is. So we're going to take the second row and multiply it by 3 over 2. So that is gamma 3. So just to recap, this is gamma 2, gamma 1 times the identity, or correction, times m, and this is just gamma 2, gamma 1 times the identity matrix, or just gamma 2, gamma 1. So gamma 3, well, this is going to be 1, 0, 0, 3 over 2, because we just imagined what gamma 3 would do to the identity matrix. And then you get 0, 3, 9 halves, right? Yeah. And then 3. And actually I'm going to make this minus 3 over 2, and then I have to add instead of subtract. Okay, minus 3, 1, minus 2, 0. And I encourage you to pause the video and make sure that, you know, gamma 3, when you multiply it, I better be recording with the correct microphone. I am. Okay. I encourage you to pause the video and, you know, actually do these matrix multiplications by hand and verify that it's correct, because I'm just talking off the top of my head here. I'm not actually checking. And then minus 3 over 2. Okay. Then, well, we're going to take the second equation and add it to the third equation. So take the first row and add it to the second row. Well, we imagine what that does to the identity matrix. That's going to be equal to 1, 1, 0, or correction, 1, 0, 1. Okay. So this is gamma 3, gamma 2, gamma 1, m. This is gamma 3, gamma 2. Gamma 2, gamma 1. Okay. we're just going to power through this. So 0, 3, leave the first row, minus 9 halves, it's going to do nothing there. And then this is going to be a 0. Take the first row and add it to the second row. So leave the first row alone. 1. Well, minus 3 halves minus 2. What is that? That's minus 3 halves minus 4 halves? Yeah, that's got to be minus 7 halves. I'm going to double check that because I don't trust me. Yeah, minus 7 halves. Okay. I should probably keep Sage open, but oh well. Okay. And then what I'm going to do is I'm going to do first of all, I'm going to do a transpose. So I want x is equal to something, y is equal to something. So I'm going to transpose these two. Well, to get that, you just imagine what that does to the identity matrix. 0, 1, 1, 0. That just transposes the two rows. Right? And so you have minus 9 halves, 3, 0, 0, 3, 1, minus 7 over 2, 1, and minus 2. Okay. So then we're going to take we're going to do two operations at once because I'm tired. And we're going to take the top equation and multiply it by minus 2/9. And then the bottom equation by 1/3. And you should verify that this is the same thing as doing one and then doing the other. And it doesn't matter which order you do it. Verify that. Pause the video, stop, and do that on your own. Okay. So we're going to get 1, 0, 0, 1. Minus 2/9. Minus 7 halves times minus 2/9 will be 7/9. And then 1/3 and minus 2/3. And if I didn't make a mistake, so here we have, just to recap again, this is gamma 6, gamma 5, gamma 4, all the way down to gamma 1 times m, and this is just gamma 6 all the way down to gamma 1 times the identity matrix. So if we've done our math right, this should be m inverse. Okay, so m, if I remember correctly, was 6, 7, 3, 2. Okay. Now let's multiply this. 6, 7. Let me give myself more room. 6. 7, 3, 2 times minus 2/9, 7/9, 1/3, and minus 2/3. Okay. Okay. Minus 2/9 times 6. Okay, I'm gonna pull up the calculator again. And I'm gonna close the color palette. Hopefully you can see this. So minus 2/9 times 6 plus 7/9 times 3. This should equal 1 if we've done our math right. Yeah, it does. It equals 1. Okay. Minus 2/9 times 7 plus 7/9 times 2. That should equal 0 if we've done our math right, and it looks like it does. Yes, this is equal to 0. And then, well, I think I can do this one in my head. 6/3, that's 2, minus 2/3 times 3, so that's 2 minus 2, this is 0. 7/3, minus 6, minus 7/3 minus 4/3 is going to equal 3/3, which is 1. Yeah, see, this is why I use the calculator, because I can't do arithmetic in my head. Okay, so at least we verified that in one direction, so this was, we computed, let's call this gamma hat times m, we computed that this is equal to the identity. And actually, if you know this, then you know that m times gamma hat is equal to the identity as well. But that's sort of a, that's a harder fact to establish, but if you know one of these, you know the other, actually. I'll leave you to check that if we do the other thing. But remember our original problem, we had m times the vector x, y, and I think, what was this equal to? Let me scroll back up and check. 2 and minus 4. All the way down. 2 and minus 4. Okay. Well, what we can now do is take m inverse. Let's just trust me that that is equal to m inverse times m times x, y. This is going to be equal to m inverse times 2 minus 4. Okay? Well, now we know x, y is going to be equal to, what was m inverse again? It's minus 2/9, 7/9, 1/3, and then minus 2/3. Okay. Times 2 minus 4. Okay, and let's just multiply this out. So x, y, let me, okay, this is minus 4/9. I'm just going to do it by hand, times 2. It's minus 32. 32 minus 32/9. And then 1/3 times 2. This is going to be 10/3. Okay, so this is going to be equal, so what we've computed is that x, y is equal to minus 32 over 9 and 10 divided by 3. Okay, that looks interesting. Let's just double check. So is that what we got before? Yeah, so minus 32/9 and 10/3. That is correct. So we got the correct answer. And I'm going to give you an interesting problem to think about, which is, so you know what m inverse is. It's this. what is the determinant of M inverse? And then just try that and see what happens, and compare that with the determinant we had for M, and then take the determinant of the identity matrix and see if you notice anything. Alright, I think that's a good first video. Just dip our toes into what's going on. And I'm going to start talking about geometry a little bit, probably in the next video. But here we have some very concrete idea of what is going on when we solve a system of linear equations. Alright, thank you. Join me in the next video and watch the first couple videos in the abstract. Watch all my videos, but watch the ones in the abstract algebra playlist. That's all. Thank you.